God damn. Okay, so here's what I'm gonna do. So I can actually type. So we're just doing this question, and the question. I might just include the question somewhere here. So where was the 27 Teen Titans? We should really change this class name to the One Piece or something. I feel like at this point it's kind of earned today. So we'll just do. Imagine the One Piece just turns out to be some dumb shit. Probably will be, eh? Okay, so here's what we're. You're looking at this problem, right? So let me just. These are always important to visualize, so I always like to visualize them for you. So let's go ahead and plop this in here. So just text it to myself. Text to save on by save on or save on. Okay, let's do this. Where's save on? Here we go. All right, you all see this? So P is the point on AB such that AP, so like just drawing this picture, you have A, you have B, and so if you take a fraction of AB, so this is AB, right? If you take a fraction of AB, it'll sort of be a scaled down version of it, yeah? KAB. Everyone agrees with that? And so you understood the sort of construction of the question? Where did you struggle when you tried it? So you said part B, right? Find the value of K for which AP, so here's it, AP is 3/2 of PB. Is that cool? This is PB. So you want 3/2 times PB. Fair enough? Now you can be sort of, you can sort of be cheeky here. So AP equals 3/2 PB. Yeah? AP is going to be final minus initial. Yeah? So KAB. So you just want to rewrite it in terms of AB. Is that clear with everyone? Like you want to rewrite it as AB. So it's going to equal 3/2 times B minus P. Yeah? Everyone cool with that? So what I'm saying is, okay, AP is here, and then you want PB, so 3/2 PB. Yeah? So if you think about it, what does AB equal to? We could just be cheeky here and just say, okay, what's AB equal to? Do you all agree that AB is the same thing as AP plus PB? Yes or not? Yeah? So PB is 2/3 of AP, isn't it? So I want to rewrite everything as, see, because I'm writing everything in terms of AP and AB. Yeah? So I don't really like having a PB in there. PB is ugly, right? So let's get PB out of there. So I can say, okay, PB is going to be the same thing as 2/3 of AP. Everyone agrees with that? And then therefore, AB is equal to AP plus 2/3 of AP. Everyone agrees with that? And that's the same thing as AB equals 2/3 plus 1, which is going to be 5/3 of AP. Yeah? So what we're saying is, if you say, here's AP, right, or 3/5 of AB. So moving that to the other side, 3/5 of AB equals AP. You see that? It's just kind of nice to sort of write this in a different way. So here's, okay, this is AB, 3/5 of it is like right there. That's the idea. Find the value of K, for which, well, what is the value of K? 3/5, right? See that? So K is just 3/5. You see it? Any problems with that? So, and that kind of makes sense as well, because if you're saying it's 3/2 of PB is AP, right? So this is PB, and then 3/2 of PB is this, and this is just PB. So 3/2 of PB, that means this is basically 3 times, there's like 3 bits for every 2 bits of this, okay? So that's like, it's like breaking it up into 5 intervals, and then writing it like that. So 3/5 of the total is going to be PB, right? Now, to just to give you a nice visual of this, because I think it's nice to sort of see what the hell this question is even talking about. So you have AB. We can draw the line from AB. So line or ray, I think. This is segments. Okay, I'm going to go to Desmos geometry. This is like a little bit better for this kind of stuff. So I can just put in A. You can still show the axis and everything. So grid axis, everything. So A is like 3, 2, 3, 4, whatever you like. Okay, put it wherever you like. And then B is 8, 1, 8, 2. I'll just change that color to be red as well. Okay, so I have these two here. So I can say the line between A and B. Or I could do, I think they call it ray or segments. Between A and B. This just draws this over here, right? And I might as well make that, oops, might as well make that one red as well while I'm at it. Cool. So you can see this here. Then I can pick P to be anywhere along the line, right? So if you think about what P is going to be, it's going to be, let's go to A first, right? And then add on K times AB, right? And then K times A minus B. Well, if I'm going to write that as B minus A, right? That's AB, and then let K be here. So let this be 0 to 1, and let's see where K is going to be. You sort of see where it is? So it's like the slider. So again, just labeling this so you can see them. This one is A, and this one is B. Yeah? So if K is 0, what is that? That's kind of like starting at A, right? If K is half, then we're halfway, right? And then if K is 1, then we're at B. See, it's like kind of allows you to move from one to the other. Is that cool? Everyone sees that? Now, this is all well and fun, but like since you guys did all this hard homework, I'm going to give you guys a bit of a bonus piece of math that's pretty cool. Okay, that you don't really So is that the only question you struggled with, or was there something else you wanted? Yep, everything else was okay. Cool. So let me show you a bonus piece of math, which is even cooler. So bonus math, ready? Bonus math. The pen tool. Has anybody ever used Photoshop? Has anybody used I'm sure you guys have seen one before, a pen tool, but let's hold on. Let's say I think there was a. Let me just show you this. So none of you guys have ever done any like used image editing software or anything like that before? Nothing like that? Seriously? That's crazy. Okay, well let me show you this. So here I have this. This is like a Photoshop clone. If you guys have ever sort of used Photoshop before, but you can just make a new. Let's make a I don't know, a new YouTube cover, whatever, right? So let's go ahead and do that. So I've got a YouTube color. I can go ahead and I can on the layer just go ahead and I don't know, create a background or whatever the hell I want. But one of the main things in Photoshop that you can see is this pen tool over here, right? So pen tool, I can sort of do this. Have you ever seen anyone do this before, like a pen tool? You all seen this, and it draws nice curves like that? Have you all seen this before? Has anyone not seen this before? So Charlotte's saying yes. Have you seen this before? Well, Chris, you haven't before, right? So this is like one of the ways. This is one of the ways that we draw nice smooth curves on a computer. This is pretty much the most common way that people do it, right? So if you wanted to draw a nice smooth curve like this, even fonts, like if you go into a font, there's your curves, right? This is a very, very common thing where like even you probably never even realized this, but fonts on your computer are also specified with these like nice smooth curves, right? So every font file is just a whole bunch of smooth curves. So one question you'd ask, like in math class, they taught you how to graph a bunch of stuff, right? Like you can graph like quadratics and you can graph polynomials and whatever the hell. But the one fun thing you might ask is, what if I wanted to draw the graph of like some random shape that I wanted to draw? Like what if I wanted to draw a random shape and I wanted to graph that? How could I do that? Right? So do you all kind of see the problem I'm trying to solve? So what if there's some random shape that you've never seen before? Like I just want to graph some random shape. Like you do agree that this pen tool is kind of a good way to do it, right? So I can kind of just go step by step and just like if I wanted to draw any shape I wanted, like if I wanted to draw a love heart, like I could go ahead and just go brand new. Like let's try a love heart, right? So I'm gonna put a point here. Okay, so I'm gonna put a point here and a point there, right? And then I'm gonna do that. And then I'm going to put the point there, and then I'm going to keep going, sort of like that. Can you also sort of see that? I made a bit of a wonky love heart because I tried to do it a bit too quickly. But I can make a new one here. So I can try again. So I can make a pretty nice one as well. So I can go here, and then I could say this is like the piece of the heart, and then I can go up here, You also see that? If I wanted to, I can even include that bit. And then I can go up like that. You'll see how I'm doing that? I can just make any shape I like. This is the basic idea, like if you ever became like a logo designer or something like that, this is how you would go about doing it. See, you can go ahead and you make that shape, and then once you've got the shape, it's really easy to do things like fill it in with a specific color and do all that kind of stuff, right? But you need to be able to define the shape before you do that, right? So that's difficult. How are we going to do that? So this is a nice side application of vectors that people don't really realize, is this idea of a pen tool or a Bezier curve. In the I think it was the 1930s, do you ever see like what cars used to look like in the 1930s versus like the 1960s, etc.? So like, let's look at old cars. What do you notice about old cars versus new cars? Let's look at old cars versus new cars. Like really old cars kind of looked a little bit like this, right? Compare them to like, and then eventually they kind of started to look a little bit like this. But what's the difference between those cars and like modern cars like a Toyota or something? What's the main difference you notice? What's the big main difference? Yeah, like see, these ones are a lot more boxy, square, boxy, etc. So the first car in the I think it was the 1960s, I think, the Renault was the first person to actually come up with this design, what we call a Bezier curve. Because if you're going to make a car, you want to be able to manufacture the car the same way all the time. You want to know the exact dimensions of the car. It's not good enough to sort of be like, give someone a drawing, because a drawing, if you get off a drawing, you're going to have like 6 copies and they're going to look different. You have to have exact dimensions on there. You know what I'm saying? So the first cars that ever came out with like these nice smooth curves were these Renault cars. Okay, so eventually, like initially, cars would look very, very boring. Yeah, and then eventually, like we just figured out how to do the maths of these like very nice smooth curves until these days we have like proper rounded edges on cars, whereas before that was basically impossible. Okay, so the question is then how are we going to do that? So the 1930s, I think it was 19. So I think I'll look up the exact when they were first done. So Pierre Bezier, he died in 1999, born in 1910. He became very famous in 1960s. And the 1960s was the first time we started to have those nice cars, and that kind of sounds about right, So you think of 60s cars, they were like all these boxes. After that, we started to get like the Beetles, the Volkswagen Beetle, and all those kinds of things, right? So all those kinds of smooth cars, right? So 1960s is when we invented the maths, which isn't that long ago, right? Invented the math for smooth curves, right? For smooth curves. So the invention of this math directly led to basically smooth curves in architecture and in design and in cars and even computers these days, right? Fonts still use these. So the question is, like, how would we do that? So the goal is pretty simple. We want to learn how to draw a nice smooth curve. Fair enough? Or like a smooth curve that looks a little bit like this. Fair enough? So the way we're going to do this is going to be pretty straightforward. What we're going to do is, I'm going to slap on 2 points. I'm going to say, okay, let's suppose that this point is here and this point is over here. This is very, very closely related to physics here too. So what I want to do is I want to imagine I'm moving in that direction there, right? And then at the end, I want to kind of imagine that I kind of make it in this way. And then I want to sort of figure out all the in-between frames, kind of like that, and make it a little animation out of it. Can you all sort of see that? That's what I'm going to try to do. This is going to be very, very clever. So the way we do this is very interesting. So let's think about this. So let's pick 4 points. Let's pick even just 3 points right now, and we'll just keep it very, very simple. And then you'll see how we scale it up to 4 points, because the math is very cool. So I want you to imagine, just like before, I have this segment, let's call it P0. I'll call this section P1, and I'll call this section P2. Everyone sees it? Simple enough? And I want you to imagine that I've got a little car moving along these at a fixed interval, so that, one car goes from P0 to P1, and then one car goes from P1 to P2. Do you all see that? So as this car is doing it, let's say that T is the interval, yeah? This point over here is going to be T times the distance from P0 to P1, right? P0 to P1. Everyone got that? And this over here is going to be T times the interval from P1 to P2. Got it? Any questions about that? So, okay, this I'm going to call this the point P01, and this I'm going to call the point P12. Okay, that's the point between them. And then what I'm going to do is I'm going to be even more clever, and I'm going to join these two together. And then again, just the same way, I'm going to take the same fraction. So here you can see this is like 1/3. Does that roughly look about right to you? That's roughly 1/3. And the same thing here, this is about 1/3 of the distance from there to there. And then here also, I've taken 1/3. Do you all see that? And what I'm going to do is I'm going to draw a nice curve. So I'm going to sort of imagine as this point moves, from here to here, I'm going to sort of trace its path. You're going to kind of see that it's going to follow nicely there. This might remind you, have you guys ever done string art at school? You ever seen that thing where you like draw a string from there to there, then a string from there to there, then there, then there, then there? Did you ever do that in school? No? Who did do that in school? Did you do? Yeah, like in primary school, you would have been like, put a bunch of nails from here to here, and then a bunch of nails from here to here, and then you connected the strings. Yeah? You've never seen that before, Charlotte? Yeah, so it's like a cool thing that some primary schools will make you do. So string. So this is a pretty common thing that people get you to do. So if you do string art, it's like that. You never seen that before? Ever? That's crazy. Yeah, so you can like you can make some pretty crazy shit. I remember when I was in primary school, they got us to literally make that sailboat. That exact sailboat right there. So it's pretty funny. It's a pretty common one. Do you all see how that would work though? Right? So the question would be then, how would I do that? So I want to be able to sort of make that nice smooth curve. So let's see it. Let's see it in action. Can we find the point P01 first, right? So the point P01, do you all agree that it's going to be the distance between P0 and P1? Is that cool? So what we're going to do is we're going to start at P0 and then we're going to move along this distance and take, t times the distance between those two, right? So if I wanted to go from here to here, what am I going to do? It's going to be, let me just write this as P01. I'll just keep it simple. I'll call this point P12. So let's see how well you've really understood the vector stuff. How would I get to this point P01, assuming that this was a fraction of t along the edge? What would we do? So we're going to start by going, so let's call it P01. What's the equation of P01? What do I do? I start by, let's say I start at this origin. I move to the point P0, then what do I do? Any ideas? So I'm going to move along the direction of P01. Yeah? How do I find the vector from here to here? Remind me, how do I find that vector? Any ideas? So I've got a vector, this is P0, this is P1, yeah? How do I find the vector that points from here to here? What do we say we do? So I've got a vector, let's say u, and I've got a vector v, and I want the vector to go from u to v. What do I do? Chris, you got this. Sorry, I'm just picking on someone at random. No, not sure? Emma, you got this. Sorry? Cosine rule? Okay, cool. No, that's not what I had in mind, no. Charlotte, do you have any idea? Yeah, you minus it. You go final minus initial. Everyone remembers that? You go v minus u. That gives me the final minus the initial. Do you all remember that? So that means this vector from here to here is going to be what? Final minus initial, which is? Remind me? P1 minus P0. P1 minus P0. Okay, and then what we're going to do is we're going to take some fraction of that. So t is going to be like how far along it. T is going to be any variable from 0 to 1. You all kind of see that? So it's like, first we're going to ask, okay, let's move along the line. Let's just move along the line. Just keep our life easy. So I got this point P0, I got this point P1, and I want to move along the line T. Is that cool? So the way I'm going to do that is I'm going to say, okay, this point here, I'm going to call it P01. P01 should just be equal to P0, right? So just move to, from your origin, move to P0, and then take a fraction of this, where T is 0 here, right? This is like kind of T equals 0 right here. That's T equals 0, and that's T equals 1 right there. Do you all see that? Anyone confused by that? So we're moving from one side to the other. T equals half would therefore be in the middle. Everyone got it? Okay, so we're moving from one side to the other. So what we're going to do is we're going to say P0 plus T times P1 minus P0. Can everyone see that? So P1 minus P0 is the one that goes from here to here. Yeah? And then I'm going to multiply by T to shorten it. Then I'm going to add on that vector, and that should get me from there to there. Everyone see that? So that equation should move me along the line. So let's see if that works. Let's start there, and then we'll make our way up to the harder stuff, right? So let's see Desmos. So I'm going to go back here, and let's do this. So let's say P0 is going to equal, let's say 3, 4. I can put it anywhere I like. P1 is going to be 5/8. Okay? I want to make them all blue just to make my life easy, right? So what I should find is that the point in between them, so let's call it P01, right? That's going to be P0 plus T times P1 minus P0. Okay? And then t could be any number from 0 to 1, and that should move between between them. You see it? So this one over here is going to be P0. Yep, and this is going to be P1. There. All got it? Any questions? So then this I can also, if I wanted to, I can draw a segment between P0 and P1. Okay, and this is what I'm dealing with here. Okay, so I've got this one here, and then I've got this point over here, which is my motion points. Okay, I can make that as thick as I like, so I can go ahead and make that like 20, so you can see it. Okay, so this is at 0, it starts at P0, and at 1 it goes to P1, right? If I wanted to repeat that again for another point P2, let's think about this. P2 would be the next point, right? So P2 would be, let's say 3, 4. I'm going to draw that as blue again. So let's say P2 is like over here, right? You all see that? Now I'm going to copy this exact same equation to find the point P02. Do you all get that? So I'm going to copy the exact same equation to find the point P02. So this is going to be point 1, 2, sorry, 1, 2. I'm here, I'm going to start at point 1, and then I'm going to go to point 2 minus point 1. You all see it? And so now this one, I'm going to also make it purple just to keep my life simple. I'll also make it nice and thick. Yep, so let's see. At 0, they both start here, and now they're going to sort of go from there to there. Can you all see it? Everyone got it? So they both move along lines. So they're not doing anything particularly interesting. They're just both moving along a line. So I can go ahead and write the segment from P1 to P2. So they're not doing anything interesting. So these are still just kind of doing their thing. Cool. So everyone can see this so far. So I'm moving from here to here and here to here. Now what I can do is I can draw the line between these two. So let's see this. So the line between these two, watch. So we're going to just keep going here. So draw the line between, right? So the line between them would be segments between P01 and P12. Okay, so that's the segment between the pair of them. Everyone gets this? So it's doing that. Cool? Yep. And then to find the line in between them, to find the middle point, I'm going to take this again, and I'm going to be really cheeky, and I'm going to call this the final point, the point I'm after, P. Here, it's going to start at P12, right? Remember, P12 is the point in the middle, right? That's this point over here. We're starting at this point over here, P12. The point, sorry, P01, that's that point there. And then I'm going to do the exact same thing where I'm going to go up by a certain amount over there. Okay, so I'm going to say the same thing here. So I'm going to say, okay, I'm going to start at P01. Then I'm going to go to the final point, which is P12. And then minus the point is P01. And look at that. Can you all see it? Kind of goes like this. Now look what the green point's doing. See how the green point's kind of moving along on a curve? You all see that? Nice? So it's moving along on some kind of nice curve, like that. Do you all see it? If I could draw the curve, then that would kind of be it. I'd be done. Do you all see it? So let's see if we can do that curve. Let's see if we can draw that curve out. Okay. So let's see. So P01 is the point P1 minus. So we said P01 is going to be the point P0 plus T times P P1 minus P0. Everyone agrees with that? If I'm going to expand and simplify that, watch this. I can write this as P0 plus TP1 minus T P0. Everyone agrees? You take P0 as a common factor. This is where it's going to be funny. P0 out of 1 minus T plus T times P1. Right? So it's kind of an interesting, this is the same equation, but it's just written a little bit differently. This idea, notice that this 1 minus T, when T is equal to 0, what happens? 1 minus 0 is just 1. Do you all agree with that? And then when T is equal to 0, that just puts 0 here and that just crosses this out. Now when T is equal to 1, what happens? If I put in a 1 minus 1, that crosses this out and makes this one equal to 1. So notice how what we're doing is we're kind of mixing, we're sort of starting at P0 and then we're mixing over to P1. You all sort of see that? It's like over time we're sort of mixing over from P0 to P1. This equation gives me a nice way to go from P0 to P1. You sort of see that? The way it works is you do 1 minus T of the thing you start with, right? So 1 minus P of the thing you start with, and then 1 plus P of the thing you end with. Is that cool? So that's P01. So let's do P12. It's going to be the same thing. 1 minus T of the thing I start with. I'm going to start at P1, and then T of the thing I end with, P2. Do you all see that? Now I'm going to be clever and I'm going to mix these two again. So I'm going to mix these two again. So the final point P, I'm going to start with 1 minus t of the thing I started with, P0, 1. And then I'm going to say t of the thing I end with is P1, 2. Do you follow? Now I'm just going to sub and simplify. Okay, so let's see. P equals 1 minus t. P0, 1, that's going to be 1 minus t, P0, plus t, P1. You'll see how I did that? So I'm just plugging that in, just be a bit careful. So I just plugged in the equation there, right? We're going to need to be careful in just a second. And then I'm going to take this whole thing and multiply it by t. Okay, so plus t. Outside of all this, okay? So we're going to expand and simplify here. Let's see this. P equals 1 minus t squared times P0 plus, all right, let's see, 1 minus t times t P1 plus t times 1 minus t P1 plus t squared P2. Do you all see what I did there? I just expanded out the brackets. Now notice that there are two of these, and that accounts for the fact that they could be in either order. 1 minus t times t and t minus 1 minus t. So then what I can do is in the last step, I can just do this, just duplicate them, say bye-bye to these guys, write this as P1, and put a 2 out the front of this. And this is cool. Do you notice this is kind of like the binomial theorem that you saw at school? Does it look kind of similar? It's like something squared and 2 times something, and then that's something squared. Do you all see that? It's kind of very similar to the binomial theorem. If I plug this in, theoretically that should just draw the curve. Let's see it. Did that work? Let's see. So I'm going to go to Desmos over here again. So I'm going to just plug it right in, right? So I'm going to go P equals 1 minus t squared, right, times P0, right, plus 2 times 1 minus t times t of P1, okay, and then plus t squared outside of P2, okay. 2 times 1 minus t times p. Oh, sorry, the squared has to go on the outside though. Cool. Look at that. That's the curve. Isn't that cool? So I can just go ahead and make all of these guys just a bit thinner, just get them out of my way. Just make them all thinner so they're all as out of my way as possible, yeah? And then that's it. So these are your control points, and then this is, so I don't actually even care about these points. I don't need to make these points so thick. I'll just make them thinner too. Make it like 10 or 5 is enough. 5 and 5. And then my last point is this green point over here, which I do care about. So I'll keep it green. I'll make it 20, and I'll make that 5, and I'll make it green again. Okay, and this is our point. So I can control my P1, put it wherever I want. You all see that? And then I can go ahead and get smooth curve like that. Isn't that cool? That's nifty. So then what I can do is it allows me to draw any shape I want, and it doesn't even have to follow the vertical line test. You know the vertical line test that you got taught in school? Notice that this definitely doesn't pass the vertical line test, but it's still, you know, it's a 2-dimensional function. This is we're sort of like foreshadowing more things that are going to come up here. But can you all see this? Does anyone have any questions about it? Yeah. So this over here is the you know, Bezier curve. Bezier curve. We call this the third order Bezier curve, right? The reason we call it a third order Bezier curve, by the way, and I'll just drop this in for you. Well, for some dumb reason, it's not, like my copy paste has not been working all day today. So I'm just having to like send things to myself. But yeah, so third order Bezier curve, I can sort of just drop this in here for you. So this is the third order Bezier curve. So you can just see that there. One way we can sort of also think about this is it's almost like you're expanding out the brackets of 1 minus t plus t squared. Do you all sort of see that? And that's how you get each term, right? That's kind of the idea. So if you wanted the next order Bezier curve, what you would then do is you would just do the same thing, but just expand it to the power of 3. Does everyone know how to expand a plus b cubed? Everyone knows it's a cubed plus 3a squared b plus 3ab squared. Everyone seen this before? Plus b cubed? Yeah? So therefore, the next Bezier curve would just be, if you just think about it, it would just be p0 times t cubed, right? Plus 3, and then times p1 times, I should just write it. I'll write it. I won't be lazy. So t cubed times p0. plus t squared times 1 minus t. I also have to start by 1 minus t, sorry, so just the same way. So 1 minus t cubed will be the first term, right? Just same as it was over here. So it's going to be cubed. And there's going to be 3 of these with 1 and so on, right? So it's going to be 1 minus t cubed times p0 plus 3 groups of 1 minus t squared times t of p1 plus 3 1 minus t times t squared of p2 plus t cubed of p3. Do you see this? And this is going to be my final point with 3 control points. So let me just sort of show you this. I don't want to go into too much depth for this one, but you could derive it just by repeating that process one more time, right? So you got this yellow point. What you could do is then just make another point here, find its midpoint again, and then connect these 2 points, and then do it again. Okay, you could do that again. If you had repeated it another time, you would see that you'd get the exact same thing, but this time it's an even more flexible one. And this is the one they use in Photoshop. This exact equation is the equation that they use in Photoshop and pretty much every 3D control program, which is pretty cool. Right, so I'm going to be a bit lazy here because it's going to get really ugly. So I'm going to just go ahead and add in a table. So I'm going to call it P. So just because I just want to be able to graph them all, right? So X, Y. Okay, so then I'm just going to do like 2, 3, 2, 4, 1, 5. I'm just going to need 3 control points, right? 3, 4. So I'm going to need to be able to drag these around. So I want to be able to drag these around. Yep. So I want to be able to drag them. And you can sort of see that. So the equation is just going to be, let's see. So to write the first point, I can just write x1. And that gives me the 2, right? x2 gives me the 0.16. You see that? So I could just write them like this. So I could just be lazy. So let's write them out. So the x equation is equal to 1 minus t squared. Yeah. So let me call it a x equation. So I've called these x and y. So let me call them. No, I don't know. I wonder something. I've never tried this before. If I just type p equals 3, 4, and 5, 2. I've never actually tried this. So let me just try this. Can I drag these? No, I can't drag them. Stuffed. Okay, that's fine. All right, so I've got these ones over here. So I'm just going to write the equation. So I'm going to call this x of the point is going to equal 1 minus t cubed. So I'm just going to write this out. x1, right, plus 1 minus t squared, right, times t, and then there's going to be a 3 there, and then I have to do x2. You all see that? Plus 3, then 1 minus t times t squared, and then x3. Okay, and then I have to go t cubed x4. Okay, that's going to be the first equation for x, right? Then I'm going to do the exact same thing for y. Right? So I'm going to do the exact same thing for y. You all see that? I'm going to just make this a function of t just to keep my life simple. Yep, so just swapping all the x's for y's. And then if nothing has gone wrong, everything should work. Okay, so this is the equation for x and this is the equation for y. And so then the point x p of t and the point y p of t is that curve. How cool is that, right? I can even just draw the segments from x1, y1 to x2, y2. Okay. So it's just a bit ugly there, but can you all see what I did there? So I just drew that, and then I'll do from x3, y3 to x4, y4, and that should be the whole thing, right? So this is kind of how you do it. This is literally the pen tool from Photoshop, see? Isn't that cool? So you could just literally draw any shape you want, just by connecting these together, right? And that's what Photoshop is doing. It just draws one, and then it just draws another one right next to it, and just draws another one right next to it as well. Okay, so that's what you do. Oh, sorry, I just realized my head is on the way, but yeah, I just drew the segment between the lines. Okay, so that's it. That's the pen tool in Photoshop. So Photoshop pen tool. Do you all see that? So it's just using the same equations that you kind of had in your homework, but then just over and over and over again, just applying them over and over. So you can see that vectors are pretty damn powerful, right? You can do some pretty crazy stuff with vectors very, very easily. Okay, so let me plug that in there. Cool. Did you find that? That's interesting. Not so interesting. How'd you find that? Right. So one of the things I've given my students homework in the past where I'm like, okay, draw. You know, it's the same stuff you get at schools, like draw something on Desmos, but obviously, like now that you have Bezier curves, you should be able to draw whatever the hell you want. Is that fair? So you should be able to, anything you can imagine. Do you guys all get the like draw something on Desmos homework? Did your school ever give you that? No? They will. They will. It'll come. But do you all see this? Any problems with this? Okay, cool. It's so funny. I'm just getting texts from myself. Yeah, so that's basically it. So this is just like taking sort of the same ideas here and sort of taking them to the extreme. You can do some really cool shit. Is that cool? All right. So that's it I have to say about that. Now we're up to the final thing, which is this idea of multiplying vectors. Now, this is where all the magic happens, I will say. Right? This is where all the magic happens, but it's magic that I don't think that you're quite primed to understand or appreciate just yet. Okay? But it is very, very cool. But it's going to be your sort of first time seeing it. Multiplying vectors. Okay, let's do that. So we want to ask the question. So we know how to add two vectors together. We know so far. You know the story so far. Just reminding ourselves. Story so far. Okay. With vectors, we know how to do a few things. We know how to add two vectors. Let's say A and B, right? To make a sum, which looks like this, right? So this is A plus B. We know how to do that. Yes? The next thing we also know how to do is we know how to subtract. So if we have A and B, we know how to subtract them. So this is going to be B minus A. Yeah? And the final thing we know is we know how to multiply it by a scalar. So if you know that this is A, this is like 2A. And then by that logic, this would be 0. 0 vector. Agreed? That's the story we've said so far, and you've seen some good stuff. And to be honest, with just what you know so far, you can already solve so many freaking problems. One other thing we saw, by the way, was the length of a vector. Right? We talked about the idea. One last thing was that we talked about the length of a vector. So we have a vector A expressed in a basis E1, E2, right? Especially Ij was the basis we were especially interested in, right? Ij. We then explained that you could always rewrite this as this, right? Ax, Ay, and we could say that the length of A was equal to the square root of Ax squared plus Ay squared, right? I think we've had a bit of a fanfare there, and that's all been fun. Has anyone been confused by anything so far? Or do you feel like everything so far has been quite easy to understand, right? So then the next obvious question is what? We're going to ask, okay, how do we multiply two vectors together? And this is a question that is very funny. Now, first question you might ask is why would I want to in the first place? Why would I even want to multiply vectors in the first place, right? This is a very valid question. So first answer is this, right? So the dude who first discovered this, his name was Hamilton, okay? William Hamilton, okay? Not the Hamilton from the movie. Sorry? No, not from Jurassic Park. Not the Hamilton from. So if you've seen there's a play called The Hamilton, Alexander Hamilton. He's one of the forefathers of the U.S., right? But not that Hamilton, but there's a different Hamilton, right? So this Hamilton was an Irish guy, and apparently he was so happy when he figured this out that he like walked up to a bridge and actually carved out his equation into the side of the bridge. And it's because apparently he'd been working on this problem for like eight or something years, and till today it's still considered one of the most important pieces of mathematics ever invented, right? Because it's really crazy how much shit you can do when you just think about like how can I multiply two vectors. Like you can't be properly primed to understand like how crazy this is. But I'm just going to give you a few things that have been made possible because of it, right? Number one, the internet. Obviously, the internet. You're going to be communicating with someone on the other side of the world, right? And you want to be able to do that really, really quickly. So what you want to do is you want to transfer information really, really quickly. And it turns out a really good way to store information is as a vector. A file, you may or may not know this, a file on your computer is just a big multi-dimensional vector. If you think about what it is, right? If you think about a cell, right? I told you a two-dimensional vector is just a coordinate of 2 points, right? Like let's say 3, 4, yeah? That's a two-dimensional vector. But if you wanted to, let's think about an image file for a second. What is an image file at the end of the day, right? Isn't it just a grid? Isn't it just a grid with a bunch of different brightness values on different places? Yeah? If you just flattened the grid out into a big long line, wouldn't that just be a big vector? You sort of see that? So that's kind of the idea. Another one would be sound, right? If you ever wanted to transmit sound, if you think about what sound is for a moment, it's just a graph, isn't it? Just the sound intensity as a function of time. So if you transmit all those numbers. So like imagine the intensity here is 0, the intensity here is like 50, and the intensity here is like minus 10. Fair enough? And that makes a big vector. Yep. That's also, by the way, how, you know, how you've ever used Spotify before? Oh, not Spotify, Shazam. You know the thing, like sometimes you're like, I don't know what the song is, and you ask Siri like, hey, what's the song? And then it knows what the song is. How do you think it does that? It's asking this really interesting question. It's asking, and this is the big question that Hamilton was interested in, is how similar are these two vectors? Like, let's say I have these two vectors. I want to ask the question, how similar are they? Okay, it's a very good question. It's a very simple question, but you know the answer is going to be quite surprising, quite interesting. Because vectors are fundamentally one-dimensional things. They're just line segments, right? And what I'm asking is like, how close are they to each other? do you kind of see that? One problem though is that if you think of like an image file, it's like how many dimensions is this? The coordinate has one number, two numbers, three numbers, 4, 5, 6, 7, 8, 9, 10, 11, 12. You get that? So if a 1 megapixel image is technically a 1 million dimensional vector, if you think about it, right? That's technically what an image is, right? Another one that we use all the time is hearing aids, right? Hearing aids, you know, you hopefully should never need one, I hope, but if you need a hearing aid, they're completely relying on like vector math to basically figure out which hairs in your ear to stimulate. You know, the way you hear is that you have these hairs that vibrate in response to sound, right? And what they're doing is they record the sound and then they figure out, okay, which hairs should we stimulate? And that's, again, something you're going to need to multiply vectors for. Another huge one is rotation. And this is the one that Hamilton was trying to solve, rotation. And I just want to show you some funny things that come out of like multiplying vectors that you probably would not expect, because that's always my favorite way to show these things. Where the hell did that go? Sorry, 1 second. Give me the tissue box over there for a second, yeah? I'm going to show you something funny. Actually, give me your calculator. Your calculator would work better. Okay? So let me sort of go over here, and I want to show you an experiment, right? So one of the funny things about this, one of the funny ideas about multiplication of vectors, it explains rotations of an object in 3D. Okay? Rotations of objects in 3D is not very intuitive. I'm going to say this to you, right? Usually when you think of rotations, you think of like 20 degrees plus 40 degrees, yeah, is 60 degrees. And 40 degrees plus 20 degrees is still 60 degrees. So the order of rotation does not matter. Correct? Okay, well, that's not true for 3D. Let me show you this. Suppose I'm going to do a turn 90 degrees around this axis and then 90 degrees around this axis. Do you agree? So top axis, right axis. Easy peasy. So here, let's start the calculator this way. Top axis, right axis, the calculator's in this orientation. Everyone agrees with that? Put the calculator back. Now, if I do this axis first and then top axis, the calculator's in this orientation. The order of rotation in 3D is not commutative. In other words, the order of rotation matters. Does that make some sense? One of the funny side effects of this is actually, it's this thing called the parallel axis theorem. And we figured this out very quickly when we were learning about airplanes, right? So if you want to keep an airplane stable in the air, it's pretty hard to do. Because let's think about this, right? This calculator has 3 axes. It has this really short axis, has this medium axis, and then it has this really fat axis. Is that fair? So if I rotate the calculator along the fat axis, let me show you this. It's quite stable, right? So it's quite stable. It can rotate nicely. Fair enough? It just rotates nicely. If I rotate it across the short axis as well, it also rotates pretty nicely. Fair enough? Like it rotates nicely. It sort of rotates in the spot. Just rotates nicely. But if you rotate it around the middle axis, so around this middle axis, and I try to throw it this way, it's going to tumble violently. Okay? Because what it's going to do is it's going to be wanting to go back to the short axis and the long axis, and it's going to get confused with like which one should I go on. And that's because of the idea that the order of operation is not, the order of rotation is not commutative. So if I do this, you can see it just tumbles like crazy. You see that? See, it's like freaking out. Always does it. You see that? Short axis, no problem. You see that? Long axis, no problem. Right? Medium axis, good luck. Good freaking luck. Won't do it. I don't care how you try. Do you sort of understand that? And that's one of the side effects of like rotation. So, you know, I don't want to get into weeds too much, but the point is, why should I learn to rotate vectors? Because it's bloody useful. It's probably the most useful thing you're ever going to learn, right? Later down the track, it'll lead you to, if you want to study higher mathematics, it'll lead you to complex numbers. Have you ever heard of complex numbers before? So if you study 4 unit, you're going to be talking about these things called complex numbers. It also leads you to the idea of calculus as well. You know how I taught you guys about calculus? I'm going to show you another way that actually gets you there using only vectors. It's really cool because I taught you calculus and it seems pretty disconnected from vectors, doesn't it? They don't seem anything like each other. And what I will show you is that you can actually recover all of calculus by understanding vectors really well, which is really freaking weird. And that's kind of going to be the coup de grace here, if we can get there today. But do you kind of understand that? So you could explain calculus really, really well. Complex numbers are going to be one, and then a whole bunch of other stuff. I don't really, like, you've probably heard before that the speed of light is constant. You've probably all heard that before. And that comes straight from vector multiplication. If you understand how to multiply vectors, you'll say, okay, well, I understand why the speed of light is constant, or has to be constant, right? So there's a whole bunch of reasons. This is just motivation. Now we're just going to shut up and calculate, so to speak, okay? And we're going to base it off of this idea. Now, multiplying vectors is going to be based off of a simple idea. Here's the idea. The length of a vector times itself, yeah, should be whatever the length of that vector is squared. Are you happy with that? Or in other words, if I multiply a vector by itself, I want its length. I want to get I want the answer to be the vector squared, right? Just the same way that when I added a vector to itself, all right, similar to, remember, when we defined scalar multiplication to be v plus v equals 2v. Remember that? So analogously, we're going to define v times v, whatever the hell that's going to be v squared. Are you all happy with that? Any problems? So this is going to be the big idea, and we're going to base everything off of this big idea. And let's see how far we can take this, okay? Can we do that? Any problems? Okay, so let's start here. Let's take a unit vector for a moment. Let's take the unit vectors I, j, and k. I, j, and k. Let's do most of our exploration in 3D, but then I'll sort of switch between 2D and 3D as we go. Actually, let's just do 2D first, and then we'll show you 3D. Okay? Let's say I and j. All right, let's ask this. What is I times j again? What is I times I going to be? What should that be? Yeah, it should be equal to the magnitude of I squared. Everyone agrees with that? I times I, whatever the hell it should be, I don't know what it should be, but it should be equal to 1. Do you all agree with that? I times I should be equal to 1. So if I multiply I by itself, I should expect 1. That's pretty straightforward. Yes? Cool. What about I times j? Well, no, let's not go there. That's too hard. Let's go easier. What about j times j? The length of j squared. Yeah? What's the length of j? It's a unit vector. So it should be 1. So j times j should be equal to 1. I'm happy with that. Okay? But then, yeah, now we're going to I times j. How the hell do I multiply I times j? I don't know. I don't know. I actually have no idea. But what I do know is let's make a random vector v out of I and j. You all agree that we can take the vector v and then write it as vxi plus vyj? Do you all agree with that? Yep. So I can always rewrite, let's say, suppose I have a vector v. I don't know what the vector v is, but I can write it as vxi plus vyj. Everyone agrees with that? So I don't know what it should be, but I should know that v times v should be equal to the length of v squared, shouldn't it? That's going to be my definition. That was my definition, right? And so, okay, well, I don't know what that's going to be on the left-hand side, but I do know how to find the length of v squared. That's easy. What's the length of v squared going to be? I do know how to do the right-hand side, but I don't know how to do the left-hand side. Yeah, but we can deal with that in just a minute. Yeah, what do we do? Well, the length of v squared, that's just, how do I find the length of a vector again? If it's vx and vy, what do I have again? This is vx, this is vy. What do I do? How do I find the length of a vector? What do I use again? Did I give you homework on this last week? How did you find the length of vectors? Yeah? Or do you remember, if you wanted, remember this is a right angle triangle. Use Pythagoras. Yeah? So v times v should just be vx squared plus vy squared, shouldn't it? I don't know what it should be, but I should know that v times v is equal to vx squared plus vy squared. That's what it should be. That make sense to you as well? Yep. Chris, you're same page as me? All right, so let's take it a bit further. Now, v is the same thing as vxi plus vyj. Okay? And then we've got vxi plus vyj. and that's going to should be equal to Vx squared plus Vy squared. Okay, let's expand the left-hand side and let's see what happens. Let's just roll with it. Vx times Vx, okay, or Vx squared I times I, right? Vx squared I times I. Everyone got that? And then I've got, what else I got? I got Vy squared j times j. That's all well and good, yep. And we know I times I is 1, we've already found that out. And j times j is just 1. We already know that, yes? All right, what else have we got? The other term we have is we have Vx Vy ij, yep. And then another term we have is Vx Vy ji. And that equals Vx squared plus Vy squared. All right, cool. What now? Right? So I noticed that I already have the Vx squared here and the Vy squared here. But then I've got these two terms that are just kind of like hanging out there and I don't want them there. So what am I going to have to do? I'm going to have to say that whole thing has to be equal to what? If it has to be 0, because if the left-hand side equals the right-hand side, this whole thing bloody well be equal to 0. Do you all agree with that? Otherwise it doesn't make sense. So therefore, Vx Vy ij equals, so let's say plus Vx Vy ji must equal 0. Everyone agrees with that? Any questions about that? Okay, so then if that's going to be the case, I can lop off these guys. I can lop off Vx Vy because they're just constants, right? I can divide both sides by Vx Vy. And then I'm forced to say that ij equals the negative of ji. Okie dokie. So this is interesting. So ij is the negative of ji. I don't know what they are yet, but I know that whatever it is, that they must be, when they're backwards, they're not equal to each other. Is that fair enough? So when I flip the order, it must somehow swap the sign. Do you get that? So this over here is a very, very important thing that we're going to talk about here. And this is what we're going to call a bivector, or a unit area. Okay? A bivector or a unit area. Is that cool? So in other words, what we're thinking about is when we multiply I times j, multiplying I times j, we're going to think of it almost like an area segment of size 1. Right? Oh, by the way, one of the other things that this does really well is if you like it, is it does the perspective. If you've ever wondered, right, why all of a sudden in the 17th century, like, you ever like looked at old art and realized that like it used to look like shit, and then all of a sudden it just started looking good for some reason? Like, what the hell happened? Did humans just like develop a new brain? No, they just developed the mathematics of perspective. Okay, that's the idea. Once we realized the mathematics of perspective, we knew how to like make things shorter as they got further away. Okay, that's basically the mathematics I used to do that thing that I proposed to my girlfriend with, right? I literally just used the maths to make that work. So prior to the maths of perspective, it was we had no idea how to draw things in 3D on a 2D plane. Is that cool? So that's another huge thing that we get out of it, which is, you know, I like to say. All right, are you all cool with this? So what I'm going to think of is ij. So now I'm going to have like I is the unit vector here. This is I. This is j. Yep. And then ij, I'm actually going to think of it as the oriented segments. Basically the unit square. Do you kind of see that? It's like the unit square counterclockwise. If this answers very clearly to you, by the way, why counterclockwise is like the positive direction in maths, right? Because you're going from I to j, so that means you're going around that way. Do you kind of see that? And if you go the opposite way, that would be considered negative, right? So a positive turn and a negative turn will kind of cross each other out. Do you kind of see that? Any problems there? All right, so that's actually quite cool. Do you have any questions about that so far? Okay, so then what we're going to do is we're going to come up with a nice simple thing. So let's talk about multiplying two vectors. Now we're ready about multiplying two vectors in general. All right, let's do that. Can we do that? So let's say that I've got a vector u, and I'm going to write that as uxi plus uyj, and then I've got a vector v, which is, they're too similar. Let's do a and b, shall we? No, fuck it, u is good. Just be careful, don't get confused by this, right? Vxi plus vyj, okay? If I multiply them together, what should that do? uv, when I multiply two vectors by each other, now I'm going to get uxi plus uyj multiplied by vxi plus vyj. Cool? So if we expand these brackets, what are we going to get? Ux, Vx, II, which we know is just 1. So I'm not going to include that. But let me just sort of like make a little table just so that we're very clear here. So I'm going to get the vector I and the vector j, vector I, vector j, and I'm multiplying them. This is the first one and this is the second one, right? The first is and the second, right? So I times I is 1, j times j is 1, right? Ij is what we call the unit bivector, so it's like this. Some people call it capital I, but you know, I'm just going to call it B for bivector. Is that cool? Or A for area, if you like. Area segments. Is that cool? And then this is the area segment as well. But usually the easiest way to write it is just Ij. Is that fair? Ij and negative Ij. Oh, sorry, Ij and negative Ij, right? Because that's the first and that's the second. Do you all kind of get that? All right, so let's do it. Ux Vx, I times I, plus Uy Vy, j times j. Cool? And these guys just go away, so I don't care about them, right? And then what we have is another section, and then we're going to get Ux Vx, oh sorry, Ux U Vy, yep, Ij, plus Uy Vx, or Vx Ux, Ji. Everyone got that? That's the whole thing. That's the whole expansion. Done. Yeah? So it's going to be UV. Yeah? Someone's happy. Okay? So then we have UX Vx plus Uy Vy. Yeah? And then we're going to have plus, okay, let's write this, Ux Vy. And then this one, when we swap their order, they're backwards, right? They're backwards. So I'm going to write this as minus Uy Vx Ij. Okay? So here's the idea here. We have here a scalar part, and then we have here a area. Do you all kind of see that, right? Now this part is going to be super important. It's going to be called the dot product. Okay? And this part is going to be important as well. This is going to be the oriented area or the cross products. I don't like to use that word so much, but this is the cross product. Okie dokie. This is going to be the idea. Are you guys all on the same page as me here? This is just like completely mathematical. Haven't really thought about this very much. I'm just doing it. Do you all see it? Any problems there? Now, in physics, this part is really related to energy. Because again, this is a physics class at the end of the day, not a maths class. So this part is going to be really related to energy, and this part is going to be really related to rotation. And that's something you're going to see over and over and over again. You're going to see these formulas pop up like 1,000,000 times over the next 2 years. Okay, so this part is going to, every time you're going to see energy show up, you're pretty much going to see this formula pop up. And every time you're going to see rotation show up, you're going to see this one show up. Okay, so you're going to see them show up in one form or another. This is not going to be the form you usually see them in, but I'm going to like to give you a bit of a physical meaning to all of these. Like, what the hell do these even mean? At the moment, we've just got symbols, so that's not really useful. So I'm going to try to give it a physical meaning so you understand well what the hell is going on here. Okay, so what I'm going to do is, remember these, and then we're going to try to understand this. Now, what did I say here, right? This, if you like, can be thought of as the area between U and V. Okay, I'm going to say this here. I'm going to just tell you the answer, and then we're going to prove it to you. This one can be thought of as the area between U and V. Is that cool? And this over here is the projected length of U onto V. Okie dokie? That's what we're going to say. So projected length of U onto V. What I mean by that, so let me sort of tell you this. Suppose we got U and then we got V, right? This one, what we're going to do is we're going to project U onto V, basically, because what the dot product is doing, or what the scalar product is doing, is it takes the part U in the direction of V, fair enough, and then it multiplies basically the length of this. So basically, we'll write this as U dot V. This is going to be the U in the direction of V multiplied by the length of V. That's going to be what it is. Okay? You might ask, okay, why the hell would I want that? But you'll see. Okay? That's basically exactly the definition of energy in physics. You're going to see, like, when we define energy for you, because you've probably heard the word energy before, but when I define energy, it's going to be literally this formula. I'm going to just pop it up on the board and be like, you're good. Okay? And that's basically it. But instead of U and V, I'm going to use force and distance. So force times distance, that's work. Okay? So I'm going to do that. Whereas this one over here is going to find the area between A and B. So say this time, if I find U and V, Okay? I'm just basically going to find the area between them. And I bet you it's going to equal this. Do you kind of see that? So the area between U and V is going to literally equal that. Do you sort of see that? That one's a nice visual, easy one, right? Basically, the area spanned between the two vectors, or the area of that parallelogram, will directly equal that. Do you all see it? So let's look at them both one by one, so we can really understand it, right? And this, by the way, easily translates into 3D. You don't need to do anything else to make this work in 3D. This works in 2D, works in 3D, works in 10D. Works just the same way. Okay, so let's continue on. Let's try. First, we're going to try the area one, because I think that's, so we're going to look at the cross product first. Okay, the cross product. Okay. Sometimes, by the way, people like to write this part as UV. They like to write it as UV equals U dot V. Okay, which is the scalar part. Okay, dot usually means scalar. And this is the main thing you need for high school. But then for physics, we need this one, U wedge V. This is the area part. Area part, scalar part. Are you all cool with that? So that's just one thing to note, and you're going to see both of them come up all the time. So let's see this in action. So the cross product is going to be the first one we're going to find. So how would I go ahead about, how do I find the area of a parallelogram? This is the first question I like to ask you guys. So let's ask, how do we find the area of a parallelogram? Because I'm going to need that in order to find the area of a parallelogram here, right? So I have a bit of a question for you guys before I start. Does that look like a parallelogram roughly? Yeah? Okay. So before I do, I don't actually care about parallelograms. I'm going to start with a rectangle, okay? I'm going to start with a rectangle. I'm going to ask you a question. Suppose for a moment that I put some hinges on the corner of each of the rectangles, right? I'm going to tilt the hinges, okay? So I'm going to tilt the hinges a little bit so you can kind of see that, like I'm going to sort of twist this one and twist this one, yeah? So that now all of a sudden it's like, it's here, and it's like here, right? You'll kind of see that? I'm going to just twist the hinges, right? So I want to ask you guys all a question. Has the area of the hinges increased? And I want you all to vote on this. Increased, stayed the same, or decreased? Do you get that? So as I sort of tilt it a little bit, has the area increased, stayed the same, or decreased? I'm going to count down from 10, and I want you all to make a vote. Okay? Because you learn more if you're wrong, so just take a vote. Do you all understand the problem? So like I start with a rectangle, and then I tilt it a little bit. The question is, has the area increased, decreased, or stayed the same? Increased, decreased, stayed the same. Okie dokie? I want you to think about it and vote on it. I'm going to count down from 10 in a few seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go. All right, so you two say stay the same. Chris, what did you say? Stay the same. So all of you think that the area stays the same, you know, and that's usually what people think, but it's not the right answer, right? So let me prove to you that it's not the right answer, right? So why did you get annoyed at yourself? I'm curious.
I felt like that was going to be the answer.
Yeah, right. Like, cause I always find it funny. Like, I actually kind of like being wrong. I don't mind being wrong, but I noticed that a lot of people when they start, they kind of, especially if they're like overachievers, they generally don't like being wrong. Like, it feels bad almost, right? But let me prove to you that it changed, right? If I was to take that triangle and chop it off, do you agree that it would sort of fit nicely there? And do you agree the width is the same, but the height has gone down by a little bit? No problems? Can you all see that or not? Yep. So if I wanted to find the area of a parallelogram, the general way I'm going to do it is I'm going to chop off this section. Yep, I'm going to chop off this section. And then I'm going to paste over here. Can you all see that? Pasty, pasty. Yes? Any problems? Okay, so then if I wanted to find the area of this parallelogram, I would find, suppose I knew A and I knew B and I knew the angle between them. That's what I know this time, right? Let's say that I wanted to find out, because, you know, like I would know the vector A, I would know the vector B, and I would know the angle between them, just like I did with the metric. Is that cool? How would I find the area of this parallelogram? Let's say area. What would it be equal to? Or I could say, suppose I knew the length U and that I knew the length V. Yeah? How would I find them? What would I do? Well, I'm going to need to find this vertical height, aren't I? Yeah? And do you agree that that angle is actually just the same as that angle? Yeah? I know that length V, so I can find that height H, couldn't I? How could I find the height H? So area, do you agree that it's just h times v? How do I find h though? Because I don't want to be dealing with h, I want to deal with u. So what do? So if I did sine theta, what's sine theta equal to? H over u. Therefore h is equal to u sine theta. Everyone agrees? So therefore this is equal to uh sine theta. Have you guys all seen this before? Yeah? This length times the sine of theta. Do you all see where I got that? Do you have any problems with that? Right? One of the funny corollaries of the area of the parallelogram then is if you were to move along this line, yeah, if you were to sort of move these corners along this line, yeah, does the area change? No, because the height stays the same, right? So if the height stays the same and the base stays the same, this one changed because the height did not stay the same. See that? The hinge down. In fact, for this one, if you go all the way down, obviously, then it would collapse into a flat line and there's no area left. That's always a very good way to think about these problems. By the way, when I give you a problem, always push it to the extreme. I'm always careful to not push it to the extreme to confuse you. Is that fair? But if you just push it to the extreme, you wouldn't immediately realize, oh yeah, it's just going to collapse into a straight line. So it would have no area left. Can you all see that? Charlotte, that makes sense to you? You're deep in thought about something? Yes? Are we all on the same page here? Any problems? So we're going to start with the cross product then. So let's think about how we would find the cross product of these two vectors. Let's suppose that I have a vector u, and then I have a vector v, right? Two vectors u and v. Yep. I know the angle between them, but I don't really know the angle between them, but I could sort of figure it out, right? I know that the area between them is going to be uv sine theta, don't I? I'm going to say like that. Cool. So I know the area between them is going to be equal to the length of u times the length of v times the sine of theta. Everyone's cool with that? How am I going to find those? Okay, that kind of seems a bit hard, right? But not really, not really. What could I do to figure this out? Now, I have a few choices. There are a few choices for me, but I could just do this directly algebraically, right? If I wanted to find the area there, one way I could do it is sort of like just by constructing this whole picture. So I could go UV. Do you all see that? Cool. So you can construct this, put that up there, put that over there, put that down there. Okay. So let's see this. Now I can break this up in two sections. So I'm going to break it here. This height over here is going to be Vy. Everyone agrees with that? This width over here is Vx. This height over here is Uy, and this is Ux. Yeah? Now since this is V, this again is just Vy, isn't it? And this is just Vx. Yeah? So how could I find that area? Can you all start to see ways I might be able to do that? How could I find the area? I could be a bit clever about it, couldn't I? I could take that triangle and move it down. Yeah? So I'm just being a bit cheeky, and because I'm lazy. I don't want to do heaps of work. I want to make it minimal work for myself. Yes? I want to make the work as easy as possible. So what I'm going to do is, I'm actually going to be clever, and I'm going to take that top triangle, and I'm going to put it, because if you think about it, where is that top triangle going to go? That top triangle is going to fit very nicely in there, isn't it? Yep. So if I was to just delete that, it's going to sort of make a nice section like that, okay? And then it's going to make a nice section just like that, yeah, by pulling that other triangle over there. But obviously I ended up double counting some crap, which is a bit annoying, but it's not too bad, right? So now, if you think about what area is sort of filled in, I've kind of filled it in like this, right? So initially, what I would have done is I would have taken the whole area and then subtracted this, and this. Do you all kind of see that? And then, but now what I've done is I've taken the whole area, yep, and then I'm just going to subtract these two, and I'm going to subtract these two. Do you all get it? But then you have to just be careful because I've accidentally double counted. So if I subtract twice, I have to add back on this section. Yeah, so I have to add back on that section. So I just add this back on. you all see it? So let's just work it out. So that's going to be Vx, and that's going to be, so you got Vx and then Ux. The width is going to be Ux plus Vx. Do you all agree with that? Because you got the Vx there, and then you got the Ux there. Yep. And you got Uy plus Vy. So Uy plus Vy, that's going to be the whole area. Uy plus Vy. Everyone agrees with it? And so then what I'm forced to say is I'm going to say, okay, the area is also equal to Uy plus Vy, yep, times Uy times Ux plus Vx, right? And then this one over here, you have to be careful. So this width over here is going to be Ux, yeah, times Uy, isn't it? So minus Ux Uy. Yep. Everyone sees that? And then I'm going to subtract off Vx Vy. That's going to be this bit. So that's minus Vx Vy. Yep. And then this height over here. So this height over here is going to be, can you see this is Vy? And this is Ux. Everyone sees it? Ux Vy. So I have to add that back on because I've subtracted it away twice. That's no good. So I have to add back on Ux Vy. Right? Plus Ux Vy. Everyone's cool with that, or does anyone have any problems with it? Yeah? Okay, so then let's go ahead and solve for it. So if I expand this all out, let's see what happens. So area equals Uyux plus Vyvx plus, what else we got? 2, I got Uxvy plus Vxuy, yeah, minus Uxuy minus Vxvy plus Uxvy. All right. So let's see. This one goes away. No, it doesn't. So any of these cross out? Uxuy, I'm not saying it. This is why I didn't want to use. Yeah, this is why I didn't want to use the same letters. 2 at the start. Uxuy. Oh yeah, there you go. They go away. Cool. Nice. Anything else? Vyvx. Okay, what are we left with? Uxvy, 2 of those, plus Vxvy. Something's gone very wrong here. I think something's gone very wrong here. Hold on, something's gone very wrong in this derivation of mine. So like I've done some mistake. I don't know what it is here. I can't see it, to be honest. But let's do it an easy way, because that way it's too complicated anyway. All right, so let's try coming up with a different way. Do you kind of understand what we want to do though, right? We want to like chop pieces away. It's probably going to just be easier to just chop the pieces away directly, to be honest. It's like too complicated if we're going to do this. So we've got these, you've got these like little cross pieces over here, and then you've got these pieces. You got this piece and then this piece. There's 2 of them, right? So you're going to chop away 2 of them, and then you're going to chop away 2 of them, right? So to chop 2 of these away, I can probably just do this very directly. Like I can not even bother with this crap, right? And then I can just make it a lot simpler, right? Because this is all too complicated. So I'm going to just make it simpler, right? So this is the whole area, right? This is the whole area. Yep. You'll agree with that? And I've also got the expansion for it down here. But I'll do it again anyway. We'll do it again. We're just going to be very direct here, and we're not going to be fancy at all, right? So then what I'm going to do, I'm going to chop away 2 groups of Vx, Vy. Do you all see that? So I'm going to chop away 2 Vx, Vy's. So I'm going to chop away 2, well, just really a Vx, Vy, isn't it? Right? Vx, Vy, because there's the one down here, and then there's the one over here, right? So join them together, that gives you a Vx, Vy. Yep. And then same thing, this one over here gives you, this one plus this one gives you Uxuy. So minus Uxuy. Okay, we're going to be quite careful with the way I write them. And then what I've got is I've got Vy, this is Vy, and this is the same thing as Ux, isn't it? Right? So minus Vyux, right? And then I'm going to subtract off this part, which is UXVy, right? And then if I didn't screw anything up here and I do the algebra, it should work this time. Is that cool? So what should happen here if I expand this out? So let's be careful this time. Ux plus Uyvx, this is the last time I will try it, plus Vyux plus Vyvx, okay? Minus all this stuff. Okay? Any problems there? So you just have to be careful, but then let's look for all of them. Let's look for all the repeats. So Vx, do we see that? There it is. Cool. And then Ux, Uy. Bye-bye. Vx, Ux. I don't see that one. Ux, Vy. Bye-bye. All right. What are we left with? Uyvx minus Vyux. Exactly what we had last time. Vx, Uy. You see that? Vyux, right? That's exactly what we had on the previous page. See that? There he is. Do you all see that? So, a bit annoying, but we proved it to you either way. So, this is the very, very important thing to say then, is that U times V times the sine of theta, right? Whatever the hell that should be, is going to be equal to Vxuy minus Vyux. Okay? This is going to be the very, very important little formula that we're going to see. And I'm going to prove this, we're going to do another example with it just to show you, like an actual example, right? Let's do an actual example so we can see it. We'll do it the hard way first and then we'll do it the easy way. So the problem I'm going to give you is, let's suppose that we have two vectors. So the first vector is going to be like 3i plus 2j. And then let's do 2i plus 5j. Yeah? And then what I'd like you to do is find the area formed by the parallelogram between them. Is that cool? You'll get the problem? So I want you to find the area of the parallelogram. Let's do it the hard way and then let's do it the easy way. The hard way, okay, the hard way would be to use uv sine theta. Okay, let's do it the hard way and then let's do it the easy way. Right? The area would be uv sine theta. Let's see. How are we going to do that? First we're going to say, okay, let's say that this one is u and this one is v. Okay, what's the length of u? How do we find the length of u? Remind me? Yep, so let's do that. Square root of 2 squared plus 5 squared. What is it? Sure. It's root 29. Everyone gets that? Then the length of v? What's the length of v? Yep, so 3 squared plus 2 squared. Yep, equals, so try these ones in your book. Make sure you guys can sort of do them as well. So you get, what is it? Root 13, sounds good to me. How am I going to find the angle between them though? That sounds crazy. How the hell am I going to do that? That sounds annoying. How am I going to do that? Anybody know how to do the angle between them? Can't really do that now. What are we going to do? How do we find the angle between two vectors? That sounds crazy. What are we going to do? Does anyone have any ideas at all?
Maybe inverse sine.
You're close. How'd you get inverse sine?
I don't know, just when you find an angle you always use the inverse.
That's true. That's true. So look, what we're going to do is like let's first, do you all agree that if we found the angle of u and then we subtracted off the angle of v, couldn't we find the angle between them? Do you all agree with that? like basically if I drew on my x-axis, if I found this angle and then I subtracted off this angle, wouldn't that give me the theta between them? Yeah. So let's do that. How do I do that? How do I find the angle of a vector? We talked about it last week. That's pretty easy to do. So if I've got a vector and it's got 2 on this direction, 5 on this direction, and I want the theta, what am I going to do? I'm going to use trigonometry. Which one do I use? Tan theta equals, what does it equal? 5 on 2, right? So the y component divided by the x component, yeah? And that's going to give me the theta, so 10 inverse. So basically the first one is going to be 10 inverse of 5 on 2. That's going to give me the angle of the bigger one, yeah? Then what am I going to do? I'm going to subtract away. What am I going to do? Subtract away. I want the angle of this one, yeah? I want the angle of this one. What am I going to do that time? Any ideas? 10 inverse of 2 on 3, right? 10 inverse of 2 on 3. Everyone's on the same page as me? Okay, so then using my formula, hard way, is going to be root 29 times root 13 times the the sine, disgusting, sine of the 10 inverse of 5 on 2 minus the 10 inverse of the 2 on 3. That should be the correct formula, right? So if you plug all of that in, what does it tell me that the area is going to be? Into your calculator. Roughly, give me roughly what the answer is. You're going to be shocked at how nice the number is. all that crap we just did. What do we get? What? 11. Oh, great. After all that. Isn't that cool? Okay. But then let's do it the easy way and see why that happened. What does the easy way tell us? Vx. What's Vx? What's Vx? 3. And what's Uy? 5. Minus? Vy? What's Vy? 2. And then ux, 2. So 15 minus 4. 11. I always love it when that happens, right? So you could do it the hard way, or you could do it the easy way. And it's like, it's up to you. But do you kind of all see that those two, it's really not obvious that this should be equal to this. That's freaking weird, if you ask me, right? That's not obvious at all. Do you all see that? Yeah? Everyone's happy with it though? Right? So it is the case, therefore, that uv sine theta is equal to this area bit, okay? We're going to talk about this a lot more in some detail later down the track, okay? But this is really cool. It means that there's a nice Cartesian formula as well as a nice geometrical formula. So there's a nice relationship between areas of parallelograms to the direct coordinates themselves, which is not obvious. I hope you can see that that's not obvious at all. But it is true, right? So I can find the area of a parallelogram just by taking the x-coordinate times the y-coordinate minus the y-coordinate times the x-coordinate. That's not obvious at all. First time I saw it, I was like, oh, what the hell? That's weird. I mean, it's not something I expect at all. Like if you understood it, it's like, you know, it's kind of hidden from you, but it's cool. Like we discovered this a long time ago, and it is a very, very useful formula. Okay. Sorry, it's just got a freeze here, so just give me a second. It's my just freezes sometimes. Oh, okay, there you go. All right, everyone's on the same page there. All right, so that's where we are. That's what we got. So that's how you do the hard example and the easy example. So that at least tells us what the cross part is doing. It's very easy. It's just finding the area of a parallelogram, and you multiply that by the unit area. This is a unit area, and this is the actual area. So this whole bit is just the area of the parallelogram. In other words, this is just the parallelogram between U and B. Do you all see that? And one way to sort of think about this is this is the scalar part, right? And this is just its ij part, right? So this is like if you have uv because u starts here and v goes here you're wrapping clockwise. So this would be a negative area. You kind of see this? So this is a really good way to do all those like area problems that you had at school, right? If you wanted to find areas of any weird composite shape, this is kind of the way we do it in a computer, right? So because this can even account for the fact that areas are negative if you go the other way. So for example, when I had a job at CSIRO, and one of the things we had to do was have maps of all the cities in Australia, because obviously we're the dudes that need to do all the science on Australian things. So like one thing they did was they wanted to find where floods would happen. Or even cooler one was like bushfires, right? We had a map of New South Wales as a vector tile. So a vector tile is just basically a bunch of vectors connected to a thing, just drawn as a Bezier curve, like I just showed you guys, right? And we wanted to ask the question, okay, where should we burn the trees, right? Where should we burn the trees to avoid bushfires in the next season? Fair enough? If we get it wrong, well, you've seen what happens when we get it wrong. So the fact that we don't have that every year is kind of cool, right? That means we don't get it wrong that often. Is that fair? Because Australia would just be on fire all the time, given the current state of global warming right now, right? It would just, like, if we didn't have the scientific tools we have these days, and we weren't back burning properly, Australia would just be on fire all the time. Like, literally, like, crazy. But anyway, funny to think about, but that's one of the cool things. So what the reason we did that is, what I'm trying to tell you is that when we, if we found the area of the fire required, the easiest way to do that would be to just use these methods here, right? And we could just write everything on an XY grid, and then we could just use these kilometers and coordinates and subtract them to find areas quickly, right? If we had to do this every time, we would be blowing up a bunch of computers. Can you all see that? Right, so that's not what we did in practice. Any questions about areas? Or do you feel like you get the idea? Right? Because this part's a little bit more dense, but it's also a lot more, what's the word? It's a lot more practically applicable to you. Is that fair? Like, this part is a lot more applicable to what you're going to be learning. This part's just kind of like, it's cool to know. It's going to be very important in year 12, so it's going to come up again. I'm not saying it's not going to come up again, but this part is like, you're going to even need it like in a few weeks. Like, you need this in year 11. Okay, so this is the work equation. So the next one we're going to talk about is the dot product, okay? So that's the cross product, which is the same thing as U wedge V, all right? And we're going to talk about, sometimes people call it the wedge product. Now we'll talk about the dot product. Okay, let's think about this one now. So, what's the dot product on about? Okay, we're going to define the dot product as, now I can do it a different way. There's a whole different way to approach what we just did. I think it's worth seeing that there's an alternative approach just for the cross product, because we're going to do the same thing with the dot product because it's a bit easier. So the alternative approach is just to say, okay, well, what's the area between the vector I and itself? What's the area between the vector I and itself? 0, right? Like, there's no area between I and itself, right? So the area between I and I should just be 0, yeah? What's the area between I and j? You have a 1 by 1 square. What's the area of a 1 by 1 square? Yeah, so I wedge j is just going to be 1. Do you all see that? And then if you did j wedge j, that's also going to be 0, right? J wedge j, that's also going to be 0. Everyone's on the same page there? So one thing you could do, if you wanted to, is you could also write uxi plus uyj, okay, wedge vxi plus vxj. Are you all cool with that, if I wanted to? And then if I expanded out these brackets, I'm going to say, okay, ux vx I wedge I plus ux, sorry, this is vy, my bad, vyj, vy I wedge j, right, plus uy vx j wedge I, yeah, and then plus uy vy j wedge j. Okay, now as you can kind of see, this goes to 0 and this goes to 0 because they just don't count as anything. And since the area is assigned, this would just become uxvy minus uyvx I wedge j. That's kind of the idea. Do you all see that? And then if we use the formula, like we could also just get straight to these from the formula. So if it was just, if you wanted the length of I wedge j, that would be the length of I times the length of j times the sine of the angle between them. What's the angle between them? That's 90 degrees. What's sine 90? Yep, sine 90 is 1. Okay, so that's just going to be 1. And these are 1, 1. So the I wedge j is 1. But then if I asked you what's I wedge I, right? That's going to be the length of I times the length of I times the angle between them. Right? What's the angle? What's sine 0? Yeah, so this is 0. And then this whole thing, these are 1, but then 0. Do you see that? So I wedge I should be 0. That's going to be the idea. So straight from the formula, you can see how the two are just like linked to each other. Okay? So now what I'm going to show you is the dot product. Dot product is even more interesting, but not as geometrically obvious, I think, a lot of the time, right? So what the dot product is asking you to do is, technically, it asks you to find the work done, or it finds the projection of one vector onto another. It's really useful if you wanted to, for example, project something from 3D into 2D. Right? If you wanted to project something from 3D into 2D, dot product is pretty much going to be the only way you're going to be able to do that. Okay, so very, very useful to do that, and it's the main piece of maths. For example, we use to calculate lighting in video game scenes, and yeah, well, dot product is used all over video games. But like, you'd be surprised. Like, do you realize when you're playing a video game, you're technically playing a graphing calculator? You're technically like giving arrow controls to a graphing calculator. It's just a very sophisticated graphing calculator. And like to sort of prove that to you, like I've done some like, Desmos is a pretty slow graphing calculator. Video game engines are very fast graphing calculators, right? So just to sort of show you like funny examples, is like you can go ahead and make 3D shapes in there, you know, and you can even go ahead and you can make, let me show you this 3D. If I draw, this is using the 2D Desmos graphing calculator. This is using the perspectives, right? So you can kind of see how it like works in perspective. So this is the 2D calculator, not the 3D calculator, right? This is just the 2D calculator, and I can like literally draw things in perspective. This is like something I do with my 4-unit students. See that? And you can kind of see that circle kind of looks like, you know. So I can do that. I can change P to increase that, and you can kind of see how that works, right? I can change the radius of the sphere, and it sort of works in 3D. And if I wanted to, I can even change the size of the sphere. So I can even bring it forward, and then kind of see it like, you know, you really get the perspective warping there. You see that? So if you're an artist, they call it foreshortening. Have you guys ever done art before? Like, have you heard the word foreshortening? Yeah. So you can kind of see it right there. Right, the maths is all right there. Maths is pretty cool. Who doesn't like maths?
Have you made the bug?
Which bug?
There's like a bug that I saw online. It's like a bug in Desmos and it moves around.
Oh, I'm sure I could. I can do some pretty nutty stuff on Desmos. So I'd be like, I'll check it out. But okay, so dot products. Let's figure this one out. So what is the dot product going to do? So if the cross product was uv cos theta, dot product, the easiest way I could say it is the length of u times the length of v times the cosine of theta. Right? The cross product was uv sine theta, right? uv sine theta. And the dot product is going to be uv cos theta. Is that fair? So that's going to be what the dot product is going to be. So the definition of it is going to be u times v times u dot v is the same thing as uv cos theta. Okay, and it's going to be calculated just the same way that we did with these two. Okay, so I mean the hard way would be to do all of this crap, just the same way, and the only difference is I would swap that sine for a tan, for a cos. You see that? That's the only difference. That's going to be the dot product. So swap that sine for a cos. That's going to be the dot product. But then I suppose there is probably an easy way, and there is. Let me show you the easy way. Okay, so if we're going to define u dot v as u times v cos theta, what is I dot I going to be? All right, it's going to be the length of I times the length of I times the cosine of the angle between them, which is 0. What's the cosine of 0? 1. This is why changing from a cosine to a sine actually changes the story quite a lot. Do you see that? So I dot I actually becomes 1. Okay? What's I dot j? Length of I times the length of j times the cosine of the angle between them, 90 degrees. What's the cosine of 90? Yeah, that makes this go away. You notice they're kind of like inverses of each other in many ways, right? So okay, if that's going to be the case, let's do the same exercise. Let's suppose I got u dot v this time. Okay, I've got u dot v. I've got uv cos theta or u dot v. That's going to be uxi plus uyj dot this time vxi plus vyj. Everyone got that? So u dot v, therefore, is going to be ux vx I dot I, ux vy I dot j, uy vx j dot I, plus uy vy j dot j. Got it? Okay. By. Sound like a Backstreet Boy. Ux vx plus uy vy. That's too easy, right? That's the formula. Basically, multiply all the x's together, multiply all the y's together, add them all up. That's it. That's how you do the dot product. Okay? That's how you do it, but then we'll try to figure out, okay, why you do it very soon. Okay? But right now, we're just showing you how you do it. Okay? So just similarly, if I was to just do the exact same problem, actual example. Okay? I'm going to click copy. Alright, the only thing that's going to change is we're not looking for the area of them anymore. We're looking for the projection. We're going to talk about what that means in just a second. Okay? So, uv cos theta, so this time the only difference is that sine theta is going to change into a cos theta. Okay? The angle's still the same, but that's going to turn into a cos theta. Can you guys please put that into a calculator for me? Sorry, it's a bit of an annoying calculation.
$60.
60? Sounds good to me. Okay, so the projection here should be 60. Let's see if that works though. Multiply the x's. Oh, 16? Right, sounds good. Okay, so then here what it's telling me is multiply the x's. So that's going to be 2 times 3 plus 5 times 2. Does that work? Does. 16. Great. Right, so just again, we have a nice, easier example. So that's, our simple actual example. But now let's actually assign some geometry. What does this mean? What does a u dot v actually do? Okay, that's what I've alluded to. So let's try that. So I've told you it's going to be, that's u, and that's going to be v, right? So let's see this for a second. I told you that u dot v should be the same thing as, it's a scalar first off, and it's equal to the length of u times the length of v times the cosine of theta. Do you all agree with that? So let's think about this for a second. So this is the length of v, right? This is v right here. So if I dropped this triangle over here, do you agree that this one over here would be v, and let's say that I knew the angle between them. Do you agree that this length over here would just be the v times the cosine of theta? Right? So the length from here to here would just be v cosine of theta. Everyone's cool with that? Yep. And then if I just multiply that, so that's v cosine of theta. Let's call this v parallel, if you like. V parallel. So u dot v can just be thought of, u dot v is just thought of as the length of u parallel, yeah, times the length of v. That's it, right? That's what it, times the length of u. So, sorry, I call it v parallel times the length of v. Times the length of u. Cool? Or u times v parallel. Maybe it's clearer, okay? So what you're doing is, you're just basically looking at the shadows. Imagine like you're looking at the shadow of v. You look at the shadow of v first, and then you just multiply it like you multiply on a normal number line. So the dot product is kind of like just normal multiplication. That's effectively what it is, okay? So you're just dropping v onto u, and then you're just multiplying it directly. Can you all see that? And then by that logic, then could I write v parallel as a vector? So let's write v parallel as a vector, okay? Do you kind of understand? It's going to be in the direction of u. You'll see that? So it's going to be in the direction of u. So what I'm going to need to do is I'm going to need to shrink it down so that it's just the right length. Do you all kind of see that? So what I'm going to do is I'm going to sort of want to think about this. V parallel should be just equal to some constant times the vector u. Do you all agree with that? And the question is just which constant would that be? Yeah? Which constant should that be? Well, I know that if I found the length of v parallel, that should equal the k times the length of u. Do you all agree with that? Whatever the hell that should be. Yeah? And so V parallel is the same thing as U V cos theta, isn't it? Do you all agree with that? So V parallel should just be V cos theta. So therefore the K value I should use is just going to be V cos theta all on the length of U. Do you all see it? Cool. And then this is then, well, I can be cheeky and then just type a length of U at the top and a length of U at the top, and then I can do something even nicer. So K, this is just UV cos theta. So this is just the definition of my dot product that I started with, right? That's just definition up there. So I can just write this as U dot V and U dot U. Now this is another funny thing about the dot product, right? What does the dot product kind of look like? Let's say I took the dot product of a vector with itself. What does that do? Right? So let's just take the dot product of U with itself. What does that do? So U dot U, what does that do? Think about it. Take the dot product of that vector with itself. What do you get? Ux times Ux, which is Ux squared, and plus Uy squared. What does the dot product do? Pythagoras. Okay? Pythagoras. And in fact, the idea is that the length of U, right, the length of U squared is just equal to U dot U. That's actually right back to the first definition that I gave you, right? So it just finds Pythagoras. It just finds the length of the vector. So what the dot product has always been doing is just finding lengths in 2D. It's like finding lengths and angles in 2D. That's the cool thing about it, right? So then if that's the case, then U, length of U, that's U dot U. So hence, V parallel is equal to U dot V on U dot U times U. Okay? That's how you would sort of write that one out. Okay, and I'll just show you that on Desmos. And I think that pretty much concludes us. Like I don't want to pump you with too much information in one day, so I'll give you some practice problems so you can get a little bit better. Well, let's just see this, right? So I'm just going to go to a graphing calculator. Okay, so let's just see this over here. So if I was to go the vector U, so V parallel, let's say U was equal to, let's say 3, 4. Is that cool? So it doesn't matter which one I use, but let's say that the vector U is 3, 4, and the vector V is 2, 8, 2, negative 1, 4. Are you guys cool with that? So this is, again, I can just draw them quickly, so just things you don't need to see, so visuals, UT and VT, okay? So just drawing them like this, right? Yep. So I just want to project this blue vector onto the red vector, meaning I want to take its shadow onto the red vector. Do you all kind of see what I'm trying to do? So according to my formula, so I can say that it should be V parallel, let's call it P for parallel. It should give me the x component is U, so it's going to be, I'm going to multiply V by some scalar. Do you all agree with that? And what was the scalar? On the top, it's going to have U dot x times what? Tell me. U dot x times what? So just looking at that thing we wrote down. So looking at that blue formula, U dot V. How do we find U dot V? Remind me. U dot V is? Uy Vy, exactly. You all cool with that? And then what am I doing on the bottom? U squared, right? Everyone gets that? So I'm projecting onto U here. So I'm projecting onto U, so what do I have to put down there? U squared. So it's going to be U dot x times U dot x, so Ux squared, plus U dot y squared. Cool? And so now this is the projection of one vector onto the other. Okay? I don't know why it doesn't... something's going wrong. Oh, because I'm projecting onto U, my bad. Okay, there you go. Cool? Can you all see it? That's the shadow of the first vector on the second vector. Right? And it can even go negative. That's fine. See how it like projects onto one? This is pretty satisfying. Come on, right? That's pretty satisfying. So this is the shadow of one vector onto the other. Okay? PET. Make that 10. You can kind of see that that's the shadow of one vector onto the other. All right? So now you can just sort of do this here, and it will work wherever. Doesn't matter where the other vector is either. Right? So you can even have the vector be longer. That's fine. See this? Vector can be longer, and it still works just fine. It's sort of almost like the first vector makes a plane, right? And then you can do it like that. So that's going to be the projection, right? If you wanted the perpendicular version, by the way, like if you wanted the perpendicular vector, like you wanted the vector from here to here, obviously you could just subtract that vector from that vector, and then you could get the perpendicular one. Okay, so that's something else you can do. So just be aware of that. So this is how you project one vector onto another. All right, so that's pretty much it. So let's just let's start setting a little bit of homework, and I'll do that there. Did you guys go okay today, or was that a bit harder, or how'd you find it? Yeah, interesting, more, less interesting. What do you guys? More interesting or less interesting? What do you guys think? Yeah, it definitely like gets very cool. Like the further I go down this rabbit hole, the cooler it's going to get, right? So if I will, last week is sort of a coup de grace, or next week is a coup de grace. I want to talk to you a little bit about the dual numbers, right? And this is basically tying calculus to vectors, right? And that's going to be kind of the last thing I say once that's all done. I've actually kind of already introduced them to you, but you just haven't probably realized it yet. But I'll do that next time. All right, but last thing I'm going to do is then just set you a bit of homework, and that's going to be it. So now, I gave you guys 8b, didn't I? 8b was pretty easy. So now we're going to talk about the dot products, component formula, and then the length formula. Is that cool? So we've just done that. That's going to be more or less all I need from you. The geometric problems are cool too. Like you can solve a few of those, but they're not super important. So I mainly want you to do projections. I'm going to skip this one because this is more maths. They'll do it in maths class, and I don't really care about them that much. So I just want to be able to do that, and then applications to physical situations, because that's going to be very relevant to physics. Okay, so this is that's going to be all I'm going to really need. Okay. So yeah, 8C. Let's just find Teen Titans here. Where's Teen Titans? Okay, so I'll just put this in here, and if you have any trouble, so make sure you read it and it all makes sense to you. I love how like I haven't gotten any responses until I said something about One Piece. You fucking funny cunts. I'm still on the second one. I watch shows really slowly because I don't have a lot of time. But I'll get around to it. It's more fun that way because then we can like talk about it slowly. So he ate a fruit. Did I spell that wrong? Exercise. 8C. Okay, so I'm just gonna expect you to do question. Let's do 1BD. Question 3AB. You just kind of have to get used to their notation, but it's pretty similar to what I did anyway. Question 6. B. Okay, and then let's just try a few others. So let's do question 8. Question 9. AC. Question 13, question 15. Question 18. Okay. I don't want you to get too theoretical. I'm not going to even give you the enrichment questions, even though like they're fun to do. If you want to try some, like you'll be preparing yourself quite well for next year, but I don't really care that much about it, so I'm not going to do that. Exercise 8D, I don't care about at all. All right, it's not useful to us, but what I do care about is the projections. So 8E. Exercise 8E. Okay, so we're going to do question 3. Then we'll do question 5, and then I'm going to do question 8. And question 11 is fun if you want to give it a go. It's like 10 and 11, so that's forgot to bold them. Okay, so that's going to be it's there. Okay. And then the last bit is 8F, so physical situations. Okay. So this one is where like you might struggle with this one because it's gonna like throw you right into the physics deep end, but you're gonna start seeing how all this crap has been applicable to physics this whole time, because so far it's probably felt like kind of theoretical, right? But hopefully this exercise will sort of make it clear to you, and why the hell I have bothered to do this, because in the past this has been a huge problem. So I just want you to be able to do a few of them. It's the maths book is pretty good because it kind of tells you how to, you know, do it to some extent. And then 16 and then 17. So you might struggle with this last one a little bit, but hopefully not too much. Okay, so you guys could do all of that by next week, we'd be golden. Okay, if you end up getting through all of this with no problem though, then we're like very ready to tackle mechanics. You guys will be bosses at that. Okay, because then I can just focus on the physics rather than focusing on the maths, which is kind of the whole idea of